Cool. Let me know if you guys can see that. Cool. Awesome. Okay, before we start, I'm just going to say, so the session on the calendar is like 1 hour 30. The session's probably not going to take that long. Most of the sessions will probably take like 20 minutes to an hour, like around that sort of time. But I've just put that in the calendar just so that they've all got that like buffer in case they do overflow or whatnot. Mentors, like all of the people who are teaching or hosting a lesson, are free to structure their lesson however they see fit. So different sessions might have slightly different structures, but however you like, after a few lessons, if you prefer one structure over another, or like how one person's doing it or something, you can mix and match. Drop your suggestions in general. I'm sure the hosts will be open to that sort of stuff. And also, if there's any questions throughout the session, please use the stage chat, which I see most of you already doing. It just makes it a lot easier because I don't have to switch between a bunch of channels. Yeah, okay. I think we're good to begin. So, data structures and algorithms. Data structures, these are the two definitions straight from the lecture slide. So, data structures efficiently organize data inside computer memory, and algorithms use data structures to achieve some sort of given goal. And then I just threw this out. So memory, this is like how I envision memory whenever I think of it. So it's like a massive lookup table, and there's a bunch of addresses, and at all of these addresses or memory locations, we might have different pieces of data. So these are the values stored at each address. Typically, each address is 8 bits long, or you could represent it as 2 hex values like this. You'll often see a hex value stored at each memory location. So this could be something like this, where each of these values represents 8 bits. And so memory is just like a massive table. You can write to the table, you can read from the table, and you can use this to kind of store different types of data on a computer. So moving on, when it comes to managing memory, there's 2 ways that we might want to manage memory. So every programming language has a runtime system. It implements this thing called a runtime system, and so every language will handle this differently. In some languages, you have explicit memory management. So this is where you have to explicitly request or release memory to and from the computer. And this is done through two sort of main commands. We have allocate and we have free. So what allocate does is it goes to memory and it says, hey, I need 3 memory locations, and the operating system will say, okay, you can have 05, 06, and 07. You can have these 3 memory locations, and they will be exclusive to the program that requested it. And then when you free memory, all you're doing is you're saying, okay, I don't need these locations anymore. Someone else can have it. So that's what these 2 commands do. And so when we're dealing with explicit memory management, it's important that we only allocate what we need to use, and we always remember to free that memory so that something else can use it. If we don't do this, if we try and use memory we don't have access to, or we claim too much memory and we never free it, this can lead to something called memory leaks. This is where we run out of memory for programs to sort of use, and it can cause all sorts of unpredictable errors, which we want to avoid. And then, so that's explicit memory management. The other type of memory management we have is implicit. So, as the name suggests, this is all done implicitly. It provides a higher level interface to managing memory, to storing and retrieving values to and from memory. So, one way we might see implicit memory management in action is with garbage collection. With garbage collection. This is where, so say we have a program, let's call it foo, because everyone does that. Foo, boom. We have I need to change the. Cool. We have a program here, and then let's say inside this program we defined variable x as 4. So this would implicitly ask memory to store 4 in some location, and then as soon as this function call ends, a higher level language that uses implicit memory management would likely return this. It would free this memory location. Because it's gone out of scope outside of this function, we don't need to access that memory reference anymore. So it kind of releases that back into the wild for something else to claim. That's just one example of where we might see implicit memory management in a higher level language. And one benefit of this is it avoids a lot of bugs and problems. It avoids a lot of headaches that might occur when you're trying to explicitly request or release memory. But yeah, a lot of common languages that we're using, like Java, JS, they'll all use implicit memory management. Everything's done behind the scenes. Whereas explicit, when you're dealing with things like assembly, you'll have to explicitly ask or request certain memory locations. You need to make sure you're not having any unpredictable behavior in your program. So it's just a slightly bit harder and more complex. But yeah, so that's memory management. If I'm going too fast at any points, do let me know. Yeah. Okay, so memory management. Now we're going to move on to a very basic data structure, arrays. I'm assuming we're all like familiar with just integers, strings. They're just primitive data structures. Well, strings maybe not so much, but they're just like the basic building blocks. And all of the data structures that we're kind of going to cover in the lessons use these building blocks and put them together into something bigger. Arrays. So an array is, again, dictionary definition, a data structure that's laid out in memory as a contiguous list of cells, with each cell indexed by the position of the cell in the structure. So all I mean by contiguous is all of the data is just stored next to each other. So let's say we had this array here, 7, 6, 3, 4. It would look something like this in memory. We'd have 7, 6, 3, 4, all next to each other in memory. And not only that, but each element in an array also has a unique index. So often programming languages will use 0 index. If you don't, there's something wrong with you. So this first element has an index of 0, and then the next element has an index of 1, and then the next element has an index of 2, and then 3. One thing to note is the index of an element is not the same as the memory address of the element. They're two different things. The memory address is where it's stored in memory, and this could be a huge number, whereas the index is the relative position inside the elements of the array. So yeah, that's the quick whistle-stop tour on arrays. With an array, there's 4 basic operations that are sort of defined, and that's array creation. So we need to be able to create arrays. We need to be able to get the length of an array, or get the size of an array. We need to be able to get values from the array, and we need to be able to set values of the array. So the creation of arrays, let's say we had an array. Okay, let's say we had an array. It's been a while since I've done this. Wait, let me. So I'm gonna see like how we can implement something like this in Java. With an integer array, we might have new int, and one thing we have to do in Java and in most programming languages is we have to define the size of the array when we initialize it. So when we're creating an array in Java, we have to say, okay, this array is going to be of length 5, and then we can't change that during program execution, because what this does behind the scenes is it calls that alloc, that allocation, and it asks memory for this much memory. We know how much memory we're going to use from the get-go, and so that's array creation. In Java, then we could do something like array dot. I believe no, that doesn't look right. We can get the size of the array with dot length. That's it. Length is an attribute on the array apparently. So yeah, cheers everyone. And then to get values, if we want to get something at index say 4, we can do this. And then to set values, again we reference the index, and then we say let's set that equal to the number 12. So Java provides these 4 sort of interfaces for arrays, which let us create, get the length of, set values, and get values of elements in the array. Now the only issue with arrays, I mean this is great, but the only issue is when it comes to, it's highlighted here, we have to have a fixed size. It has a fixed length. Not only that, but the actual types we can store in an array are quite inflexible. They have to all be integers, or all be strings, or all be floats. And one way to get around this is having different other types of data structures. So we're gonna move on to linked lists. Linked lists, again, they don't remove that type limitation. We still have to kind of have things as the same type with a basic linked list implementation. But these are all made up of what we call nodes. Linked lists are made up of nodes, and here's a graphical representation of it. The idea is we have nodes, and nodes connect to other nodes. We can create these nodes on the fly, meaning we don't have to say, okay, there's going to be this many nodes right at the beginning when we create it. Instead, whenever we want to add a node, we just create a new node. We request some more memory, and then we use something called a reference or a pointer, which points to another node. So let's say we have this. Let's say we had a single node. This is just a Java or object-oriented example of how we might implement it. We create a new node called head, and a node has two attributes. So it stores a value, which is the actual thing stored in the node, and it stores next. This is a pointer to the next node in the list. And initially this is just a list of length 0, and we've just got the value 2 in here. And then what we might want to do is we might want to add another value. So how we can do that is we can create another node, and then we can use head.next. Head.next will point to this attribute here. And we're setting that to a completely new node. So we're creating a new node, and then head.next is pointing to that new node. And so what that means is, with this original reference, with just head, we can access both of these nodes, because we can access this one with head, and we can access this one with head.next. And then to create another node, I mean, this wouldn't be how you'd do it in code really, but what we could do is we could say head.next.next equals new node. So we're saying head dot, whoops. So we're saying head dot next, which is this node. So now we're referencing this node. This is head.next, and then we're calling .next on that, which is this node, and we're setting that to a new node with value 5. So we can programmatically create a list by saying, okay, this is our first node, and from there we can reach every other node by using this next value. And it almost creates a chain of nodes, a chain of values which we can traverse across. So that's how a linked list would be sort of implemented in a high level. Okay, so linked lists, there's a few methods which we kind of covered in lectures which we should be aware of. Checking if it's empty, removing the first node, getting the value at an index, inserting at the end of the linked lists, or deleting from the end of the linked list. How do you do it in practicality? Oh yeah, so if we want to do it in practice, what I'm going to do is I'm going to write out some like pseudocode in a second for these. So adding at the end of the list, inserting at the end. How to connect this to my speaker? I'm not sure, Ivan. Sorry. So I mean, I'll write out some pseudocode in a second to explain how that would work. But before we look at these methods, I just want to introduce you to a few mods and DLCs for linked lists. So we might have a linked list with a pointer to the last node. That's another type of linked list, where instead of just pointing to the first node, we have a few nodes, and it points to the first one and the last one. This means it can be easier to get to that last node without having to go here and then do .next. Nice to hear, Ivan. And then doubly linked lists. This is where we have all our nodes, but they store the previous node as well. So, I mean, one benefit of this is we can traverse backwards. We don't just have to use .next. We can also use .prev to go back. A circular singly linked list is where we have a list, it points to the next one, and then this one points to the next one, and this one points back to the first one. So we can go round the linked list. If we're at the last node, we can go back to the first node in one step. And then a circular doubly linked list, you guessed it, is where we point to the previous one as well in both directions. So all of these different types of linked lists are just adding more attributes to each node, which let us do slightly more stuff with it. I see some people are typing. If there's any questions, let me know. But let's try and see how we might approach these. So since I was asked about this one, let's look at this one first. Inserting at the end of a linked list. So if we want to insert at the end of a linked list, let's think about how we do it graphically, and then let's think about how we might write some pseudocode for that sort of algorithm. So let's say we had some values in here, 4, 7, 2, and this is pointing to this node, this is pointing to this node, and this isn't pointing anywhere. Okay, so if we want to insert, why would you want a circular linked list? I mean, I'm not too sure about the, oh yeah, that's a good point actually. Yeah, if we reach the end, yeah, we can just keep going round without having to sort of go back. Yeah. Is it the same as... can you use .next as many times as you want? In terms of efficiency of accessing a value, is it the same as doing array I? No. So doing array I, this is a lot more efficient than doing .next, like so on. Because this is, we've already got an index, and when we're doing this with an array in Java, for example, I is just looking at the first memory location of the array. It's adding I. So say the first memory location was 0x0f, and we're doing array 1. It will just, well, let's do array 16. Wait, is that what we want to do? Let me think. Yeah, let's do array 16. So that will add to this memory location 0x1f. We know this is the element at array 16. If this is array 0, array 16 is here. So all Java's doing is it's just going straight to this memory location. And so indexing an array can be done in constant time. Whereas if we want to get an element in a list at a certain index, we have to traverse through all of the .nexts, making it linear time. Yeah, but the thing is, if we in a list, it might not be stored next to each other. So if we had something like, if we had a list of elements, it might look something like this. Let's say we had the list 1, 4, 7, 2. It might be 1's here, and then 4's here, and then 7's here, and then 2's here. And because there's a next pointer, I mean, it points to the right place, but the issue is it's not stored contiguously in memory. We can't guarantee that with a linked list because we're constantly creating new nodes on the fly. We follow the next address. Whereas with arrays, we know that they're all stored next to each other, so we can just add an offset of this first memory address to decide where to look up a certain value. Yeah, no worries. But yeah, so arrays are more efficient in certain things. We'll fill this in as well at the end. But inserting at the end, okay, so we know that we want to do something like this. We want to find .next until there's no next node, until there's nothing here, because that's where we want to insert the node. So one way we could do it is we could say, okay, let's say this node is called head. Okay, and then we create a pointer to head, and we say while ptr.next. So all this is saying is while ptr.next is not equal to that's Pythonic. Okay, yeah, let's say null. Okay, while the next element isn't null. So all this is saying is while there's some node after ptr, and then we're going to set ptr to ptr.next. So no, we've not lost the reference to head. Head is in a different variable, but this ptr is equal to ptr.next. And then after we finish this while loop, that means that there's no node after it. That's where we want to sort of add our extra node. Let's say we want to add the value 5. So what we can do after this is we know ptr is pointing to the very last element at the end of this while loop. So we can say something like ptr.next equals new node with the value 5. and that's how we'd add at the end of the list. So let's say we had PTR pointing to this first node here to begin with, because PTR equals head. Okay, while PTR.next is not equal to null, is this .next equal to null? No, it isn't. So let's move forward. Okay, is this .next equal to null? No, it isn't. So let's move forward again. And then is this .next equal to null? Yes, it is, because this node isn't here yet. And then we go on to this last line. We exit the while loop because this thing is null, and we say, okay, PTR. So this is PTR .next equals new node. And so that's how we'd add something to the end of a linked list. Again, to sort of add something to the beginning, or let's do remove from beginning. If we want to remove from the beginning, let's say we want to remove that first node, all we have to do then, in a high-level language like Java, is we can just say head equals head.next. All that will do is it will switch this head to here, and I mean this will automatically cease to exist because garbage collection will come along and say, okay, nothing's pointing to this, let's get rid of that. So this will get garbage collected, and that will be dealt with implicitly by Java's runtime environment. But yeah, this is how we just get rid of the first node. One thing we might want to make sure of, though, is first checking if head is null, because if it's an empty list, head will just be null. It won't point to any list nodes. So we might want to do something like if head is not equal to null, only then can we safely get rid of the first element, because we know one exists then. But yeah, will this be the same case for circular linked list as well? With a circular linked list, so with a circular linked list, it gets slightly more complex. I don't think we need to know that exactly, but I mean we can have a think about it. So if we have node pointer, so let's say we had something like this, and then we wanted to get rid of an element. Okay, so let's say we wanted to get rid of this one. I mean, we'd have to update this with this .next. So we'd have to set this to this, and then we'd have to go all the way around until we find the thing just before this and update this to point to this as well. So we'd kind of have to, it would take at least O of n. Make sure to talk about end as well. Ooh, yeah, okay, right. So with a linked list, before we created this node, what this would be doing is it would be pointing to end. End is just sort of, I mean, you could say it's a constant. It's just what we say something's equal to if it's not pointing to anything. And in the same way, like this list, before we create another list, this will be pointing to end. This will be pointing to end. But yeah, end is just essentially equal to null. It's just in Java, we'd implement that by just saying this .next is equal to null. But end is a good way of thinking about it in an abstract way. Yeah. So yeah, this is something like a circular linked list. And to remove it, yeah, it would take slightly more than O of n. But let's fill in this table. So with an array, accessing data by a position, what would be the complexity of this for an array, and what would it be for a linked list? Constant for an array, good. I'll put O of 1 and O of n. Okay, yeah, nice. And then searching for an element. If we want to search for an element in an array or search for an element in a linked list, we'll assume that they're unsorted just for, yeah. What would the complexities be if we want to search for something? Yeah, both O of n, good. Yeah, both linear. Okay, linked lists. If we want to insert something at the beginning, what do you think the complexity of this would be? Whereas in an array, if we want to insert at the beginning, Yeah, good. So with an array, O of n, with a linked list O of 1, the reason for that is because if we want to insert at the beginning of a linked list, all we have to do is we have to create a new node and then say this dot next equals the list, and it will automatically. We're just doing this thing once. We're just updating one thing. Inserting an entry at the end. Oh yeah, and with an array, it would be O of n because we have to shift every single element up one to make space for that entry we're inserting at the beginning. Yeah, so to insert at the end, with a linked list, we'd have to traverse through every single node. Again, we'd follow that pseudocode we wrote, and same with an array actually, because we'd have to copy everything to a new array n times. So in a linked list, can we access any element by directly referencing its memory address? It's sequentially accessed with only the list's first element stored. Oh right, that makes sense. So with an array, if we want to access, an element at index 3, for example, let's say array is stored in memory location 100. I won't use hex for now. We'll just say array is stored in mem lock 100. Array 3, the element at index 3 will be stored in memory lock 103. So we can just directly read whatever's in memory at this location. Whereas with a linked list, if we want to get list 3, what we'd have to do is we'd have to go to the first element and then look at the dot next attribute on that to get to list 1, and then we'd have to do dot next on list 1 to get to list 2, and then we'd have to do dot next on that to get to list 3. So with a list we'd have to do it linearly, because we can't guarantee what memory location it's going to be at, whereas with an array, because it's stored contiguously, we can just add to 100 whatever the index is, and we know that it's going to be at 103. No worries. Okay. Right, inserting an entry at a certain position. So with an array, again, this would actually end up being O of n. It's just the same as sort of inserting at the beginning, but we don't have to shift all of them, we just have to shift a few of them, depending on where we want to insert it. With a linked list, insert at the end of an array. I guess it depends on how you implement it, because it depends on what the language lets you do, but if there's free space, it could be O of 1. I'll just put a star next to that. But yeah, I see what you mean, because I guess it's contiguous. If there is a memory spot free. So it depends on how much memory you've got allocated for your array. But yeah, I'll put both of them and a star next to it. But yeah, with a linked list, if you want to insert at a certain position, again, it's O of n. You can almost think of it as if we have these two nodes and we want to insert in the middle of them, we have to point this to a new node, point this to that, and then sever this connection. So we just do that, and then we traverse through the rest of the list, which is just O of n. Deleting the first entry of a linked list, versus array and linked list, what do you think the complexities of these two would be? So linked list, it would definitely be constant. Array, I think it would be constant. Since I guess you can just, it depends on the implementation again. A lot of these different languages will sort of implement it differently. So it depends on what language, what runtime environment you're kind of using. If you decide not to shift all values, then it's O of 1. Yeah, again, it depends on how you're using the array. Do not need to shuffle the memory addresses down. You can just change the reference that the first element points to, I guess. Okay, deleting entry I. So if we want to delete something at entry I, what is the array versus linked list time complexities? Yeah, so for linked list O of n, for array, I'd probably side with O of n for an array, because it's highly unlikely that an array is going to be of any use if you've got like a gap in the array, I guess. But again, yeah, it depends on whether you're having, like, what kind of values you're storing in an array. If you're only storing positive integers, I mean, you can do array I equals null, but then when it comes to sort of getting a value at a certain index in an array, with that like memory location sort of predictability that I showed you, this might then render that useless, because it will kind of create gaps in the array, so it defeats the purpose of having contiguous elements stored next to each other. So again, I think this one depends on what you're using it for. How would you oh man, I'll go through that in a second, don't worry. Concatenating two lists with an array, I'd argue it's possible to do this in I mean, it depends on if there's space, but you'll likely see it done in O of n time, where you loop through all of the nodes. And then with the linked list, yeah, Witty, you'd need to shuffle everything down. And then with a linked list, concatenating two lists, I'd say this would have to be done in O of n, just because you'd have to loop through one of the lists to get to the end, and then join the next list to the end of that. Is an array a type of list? No. So a list is a dynamic data structure, meaning it can change size, whereas an array is a fixed size in memory of contiguous cells, memory cells. For inserting at the beginning of a linked list, let me quickly go through that. So if you have some nodes, 5, 4, 7. Okay, so let's say you had a linked list like this. If I want to insert a new node at the beginning, I'd do something like new equals, let's not use the keyword, new node equals new node, and let's say I want the value 6 in here. And so if we want to create a new node, so this will create a new node in memory somewhere with the value 6 and a pointer, just pointing to nothing right now. This will create this. And then what we want to do is we want to set this dot next. Let's say this was just called head. We'd set new node dot next to head. So this would create a pointer from new node to head. And this would essentially add this to the beginning of the list, because then what we can do is we can say head equals new node, and what that will do is then shift this head variable, this will shift this to then pointing to this, and what we've essentially done is we've created a new node at the beginning of the list. I'm supposed to see arrays as homogeneous, but lists is if that's to do with like the different types we can store, I'd say both of them are homogeneous by their default implementations. Example list of numbers. Yeah, both of them should kind of be seen as like one type, because it's unlikely we'll be playing around with them in an array data structure. I mean, both homogeneous in a linked list, because often, like in Java, you're going to have something like int val and then node next. Like this is going to be fixed for every node. Yeah. According to the DSA slides, an array and a linked list are type of lists. I mean, I wouldn't fully agree with that. It depends on what you call a list, but I mean, yeah. No, I see what you're saying, Ivan. But yeah, I'd say just to like clear the confusion, I like calling linked lists or dynamic data structures lists, and then if it's a contiguous sequence of cells in memory, I'd call that an array. But I mean, yeah, there's a bit of a line there. But yeah, that's the end of the slides. Are there any questions about anything? I'm happy to go through anything people are unsure about. Also, if you want to ask a question on stage, just like, I think you can request to speak and I'll bring you up. Sets. Yeah, Python uses lists. I mean, yeah, the way Python implements lists is they don't enforce a data type, so it's not exactly just a primitive. Well, it's not a basic linked list. They have different types you can store in the linked list. Yeah. Circular doubly linked lists, sure. So with a circular doubly linked list, we have a bunch of nodes. And every node stores prev, val, and next. So it stores whatever's previously before it, it stores what's after it, and it stores a value. So what this means we can do is we can do something like this, where from any node we can get to the one before it, or we can get to the one after it. And if we reach the last node, well, I say the last node, if we reach this node here, we can go back round to this node. That example's a good example of one. Concatenating lists in arrays. This is just like this is just another variable pointer to the list. I could just theoretically get rid of this and just call this variable, but it just makes it clear what the kind of... I think it just makes it clearer because that's a pointer to that. Yeah, so variable.next is the pointer. So variable.next would point to this one, if that makes sense. Variable.val is 4, variable.prev is this one. Concatenating lists in arrays. Concatenating, if you're talking about concatenating two arrays, I'd loop through one of the arrays. I'd loop through one of the arrays and sort of add it to a new array, and then loop through the other one and add those elements to that new array as well. So the prev address of the first element. So in a circular doubly linked list, prev in this element would point to the end of the list. Well, to the last element. So you need to traverse half the list. So it makes that more efficient. But then again, you technically aren't sure how much you have to traverse. If it's bang on, like you don't know whether it's going to be close to the first half or the last half. So either way, you have to traverse the whole list. It's still kind of linear. Yeah. I mean, when it comes to inserting at the quote-unquote end of the list, I mean, you can just go to the first one, prev, insert, and then next. So it makes it possible to insert in constant time at the end of a list. I mean, that's the only benefit I can think of off the top of my head with a doubly linked list. Instead of having to go all the way to the end by like looping through to the end, you can just insert in constant time at the end. Nature. You could have another pointer at the end by external reference. So that's actually another type of linked list which kind of achieves the same thing. It was the linked list with a pointer to the last node. So that would just be two pointers, one to the first node, one to the last node. They can't have different data types. Yeah. I mean, they could have different data types. Again, it depends on how you implement it. But I mean, the way we've learnt it, I think we've not really focused in on that. It's just sort of, they store values. Linked list with 2 pointers. Yeah, so that would be an example of that. Cool. But yeah, that's the end of the slides. If there's any questions, any feedback on the lesson, like how could it be better? I'm also going to stop the recording, and I'll try and upload this as like an unlisted video or something, just so anyone who couldn't make it